Here we go. This one's, I don't think, going to take us too long. We just need to kind of wrap up one concept that goes along with stuff that we've already talked about. So there's nothing really new here. It's just applying what we already know to KSPs. We're going to talk about Q again. You guys remember Q? It's been a while, but Q is basically you're plugging stuff into the equilibrium expression, except it's not the equilibrium expression because this represents the reaction when it's not at equilibrium yet. Okay, and there's two reasons you wouldn't be at equilibrium when you're talking about solubility. One, either you've got a solid at the bottom and not all of it has dissolved that can fully dissolve, so you have an unsaturated solution, or the second reason might be if you have some ions in solution and they have not yet fully precipitated. Okay, and so those are the two directions that you might be going to reach equilibrium. So yeah, again, expression of the non-equilibrium concentrations. If you compare the Q to the K, then we'll know which direction this reaction is going to proceed. Okay, so again, we've talked about all of this. Now we just need to talk about it in terms of solubility. All right, so here's an example. We got equal volumes of 1 times 10 to the negative third molar BaCl2 and 1 times 10 to the negative fifth molar Na2SO4. KSP for the BaSO4 is 1.1 times 10 to the negative 10th. Will the Ba2 plus and the SO4 2 minus combine to form a precipitate? Now, if you look at your solubility rules, barium sulfate, I believe, is one of those that is insoluble. Okay? In other words, it's one of the ones that will form a precipitate. So if you're just, straight memorizing off the chart, okay, this will precipitate, right? But the thing is, there has to be a certain concentration of the Ba2 plus and the SO4 2 minus in order for that precipitation to occur. Okay, otherwise there's not enough ions in there for it to precipitate because those ions can stay dissolved. So what we have to do here is basically figure out our Q for this reaction. Okay, so we have our concentrations here. 1.0 times 10 to the negative fifth and 1.0 times 10 to the negative third. Okay, and then we have to be a little bit careful about this. Not so much on this one, because it's the Ba and the SO4 that are combining. Now, if it was, now again, the NaCl would never combine to form a precipitate, right? But notice there are 2 sodiums in that compound and there are 2 chlorines in this compound. So what does that mean about the molarity of those 2 ions? They're double the number that's up here, right? But with the barium and with the sulfate, we're okay. The concentration that is given to us is actually equal to the concentration of the barium ion and the sulfate ion because there's only one of each of those in the formula. Okay, so you just have to watch out for that. So what we have to do here is think about our equilibrium expression for this one. And our equilibrium expression here is BaSO4 is in equilibrium with Ba2 plus SO4 2 minus. Okay, and this one's not too bad. This is all one-to-one stoichiometry, so when we write the KSP for this, it's just going to be the concentration of barium times the concentration of sulfate, which is 1.0 times 10 to the negative third times the sulfate, 1.0 times 10 to the negative fifth. Okay, and when we multiply those two together, shouldn't have to use a calculator for this one. 1.0 times 10 to the negative eighth. Okay, that's our Q. Now, how does that compare to K? It's bigger than K, okay? Which is bigger than K. KSP, I guess I should say. Alright, so let's think about this for a second then. If Q is bigger than K, then what direction is this equilibrium going to go? We've got to reduce the amount of this and this in order to reach equilibrium, right? Okay? So if it goes this way, what happens? What are we going to see when the reaction occurs? We're going to see it precipitate. You see how that works? Okay. So, yes, the answer here is yes, they will form a precipitate. Okay? That's kind of how that works. Now, what if the Q had been less than K there? Then the reaction would have needed to go to the right in order to reach equilibrium, which means that the ions are going to stay separated or separate. Okay. To some extent, when you have the other way, it really can't ever reach equilibrium. If you've just got a few ions in there and there is no solid at the bottom, then it can't ever get to equilibrium. Okay, which means that there will never be a precipitate at that point. All right, so here are the possible relationships here. If the Q is bigger than KSP, which we just talked about, the precipitation will occur until the two are equal. Okay. If Q is equal to KSP, then it's already saturated, it's already at equilibrium. There's no net movement there. Okay. There's movement, but there's no overall net movement. If Q is less than KSP, then if you have a solid at the bottom, that solid will dissolve until the Q equals the KSP. Alright? So that's kind of the way that works. Alright, so then another question here. Will precipitate form 1.10 liters of 8.0 times 10 to the negative third molar, blah, 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 blah. Okay, so we're adding these two things together. And this time it's just saying KSP for the precipitate. So now we do have to think a little bit about our solubility rules to figure out what the precipitate is going to be. Okay, it's definitely not going to be NaNO3, right? Okay, Na is a loser and NO3 is a loser, so yeah, it's not going to be that. Okay, so it's got to be PbSO4. So when those two things combine, here's the other problem with this one. We need to think in terms of concentrations, but we're adding two volumes together, so what's that going to do to our concentrations? It's going to change our concentration, so you have to be careful there. That's why they're giving you the volumes there. And sometimes, when these problems are nice, they'll just have you adding a solid into a liquid that already exists, and they'll say, assume there's no volume change. Okay. Now, that's probably not really the case, but those are the kind that are nice because then you don't have to worry about the volume changing. But on this one, we're pouring two solutions together, so we're definitely going to change the volume. So it's probably better to think in terms of moles initially here and then figure out what our new concentrations are going to be. 0.1 liters. Okay. Oh, I can do that in my head. So that's, we have 8.0 times 10 to the negative fourth moles of the Pb2 plus. Right? You guys with me on that? I just used the molarity equation, right? So we've got molarity and we've got our volume in liters. So you just multiply the two together, okay? Alright, so then we've got moles of Pb2 plus, and in order to find the concentration of the Pb2 plus, we need to divide that by the liters, total liters of solution. So how many total liters of solution do we have now? We have 0.5, right? So, let's see if I can do this in my head. 16 times 10 to the negative fourth. Is that right? I think that's right. I'm really working on my mental math here. Yeah, that's right. Okay. So then we've got 5 times 10 to the negative third molar Na2SO4. And again, we decided that the SO4 is the part that we're worried about here. So this one, you take the 0.4 times 5 times 10 to the negative third. You're going to get 2 times 10 to the negative third. Is that right? Yeah, okay, I guess that's right. That's the number of moles of the SO4 2 minus we have, because again, this is just, it's a 1-to-1 ratio. There's only one SO4 2 minus in that compound, so Then we divide that by the 0.5 again. And this one I can definitely do. 4.0 times 10 to the negative third. Okay. So there's our two concentrations. Once we finally have those, then we just plug that into our Q expression and see how the Q compares to K. So Q equals, and again, this is just our equation here, PbSO4. And I know this isn't really the direction that it's happening, right? I mean, really what's happening here is we're putting the two ions together, and they're going to precipitate or not. Okay, we have to figure out which. But you always want to write the solubility equilibrium the same way. Okay, it's just simpler that way. If you write it in the other direction, then you have to do 1 over the K, because this KSP is assuming that you're writing it this way. It just gets complicated, so just write it like this because it's easier. Okay, so there's that. So when we plug these into Q, we have a 1-to-1 ratio here, so we're just multiplying the two of them together. 1.6 times 10 to the negative third times 4.0 times 10 to the negative third. And I'm getting 6.4 times 10 to the negative sixth. Okay, which again, that Q is still bigger than our K, right? So the same thing is going to happen here. This will form a precipitate, okay? So all that work, the answer here is yes. That's a good question. Yeah, good question, and you probably know what the answer to that is. If you just say yes, then you probably won't get much credit for that, if any. You might get, well, on that one, honestly, on that one, because you got a 50-50 shot, if you just put yes or no, I probably wouldn't give you credit for it. You got to show me that you know what you're doing. Yeah, I know you are. Okay. So, selective precipitation of ions. This is kind of we're going to do probably a lab that involves this at the very end of the year. This is one way to identify what ions are actually in a solution. You can take it through a series of reactions, and certain ions will precipitate with other ions, and so you can kind of, one at a time, you can precipitate things out of the solution and figure out what's actually there, okay? Or it's a way to separate. Let's say that you want a solution. Okay, so this is an example right here. You've got, I guess I was trying to come up with an example, but I don't need to do that because I've got one right here. You've got silver and copper ions in your solution, and you want to separate those from one another. If you add HCl into a solution, the Ag plus is actually going to react with the Cl to form a precipitate, AgCl solid. And we talked about that earlier in the year a little bit, that sometimes you can add chloride ions to a solution and figure out how much silver there actually is in that solution. The copper 2 plus will not precipitate with the Cl. Okay, so the copper is just going to stay floating around as an ion in that solution. And so it's a way that you can actually, you know, if you want to get rid of the silver in that solution and have just a solution with copper 2 plus ions for whatever reason, then you could do it that way. Okay, so it's called selective precipitation, and that's all based on the KSPs for each of these different things. Okay. All right. So here's an example. Let's say that we've got a solution that has silver ions and lead ions in it. Okay. Now the thing about this one is Cl minus. I may have changed this. Does it say slowly on your paper? Okay. Yeah, I decided this is kind of a bad question. This last part, which salt precipitates first, unless we're adding this very slowly. Okay, because if you dump it all the chloride in at the same time, then you're not going to be able to really see this. But if you're adding it slowly, then you'll see one of them precipitate first, and then if you keep adding, you would see the other one precipitate. All right? So we've got Ag plus and we've got Pb2 plus, and we're adding chloride into the solution. And there's our KSPs for both of those. What concentration of Cl minus is necessary to begin the precipitation of each salt, and which one precipitates first. Now, is this as easy as looking at the KSP and deciding? Yeah, that'd be nice, wouldn't it? Here's the thing that's going to throw this off. Ag is a 1 plus, Pb is a 2 plus, all right? So that means the stoichiometry for these two reactions is going to be a little different, which means you can't just compare the KSPs right away. Yes, sir? If they were the same. Okay, if the stoichiometry was the same for both of those, then you could look at the KSPs at that point. Okay. I mean, these questions tend to try and trip you up in that particular area. So, yeah, so you got to just watch for that. It's always better just to be sure to go ahead and write out the reactions for each of these, all right? So the AgCl reaction here is going to be AgCl solid in equilibrium with Ag plus Cl minus, okay? And then the corresponding KSP for that one would be, I'm just going to go ahead and write it in general first, and then we can plug in here in a minute. All right, so there's that one. And then the PbCl2, Pb2 plus 2Cl minus. So when we write the KSP for that one, we have to square it. Okay? All right. So we basically have two x's to solve for here in order to figure this out. We know the KSP, we know the silver concentration on the first one, and then we know the KSP and we know the lead concentration on the second one. So we're solving for the chloride concentration for both. Okay. So the first one, you plug it in. I'm just going to do this right above it because this is a simple one. Let's see here. Our KSP for AgCl is 1.8 times 10 to the negative 10th, and that's equal to 2.0 times 10 to the negative 2nd times the Cl minus concentration. Okay. So when we solve for that, for this top one here, and again, I'm just going to write this up here so that I have room to do the other one on the bottom. Cl minus concentration will be 9.0 times 10 to the negative 9th, if I'm doing that right. So that's the concentration of chloride that we need in order to make the AgCl start to precipitate. Okay. And then for the second one down here, we've got Pb, or KSP of 1.7 times 10 to the negative 5th. Whoops. Did that wrong. Sorry. This is supposed to be 1 times 10 to the negative 2nd. I got my numbers mixed up here. And that just looks funny because that's so far away from the 0. Okay, so 1.8 times 10 to the negative... Actually, this is going to end up being 1.8 times 10 to the negative 8, isn't it? I think that's right. Let me double check just to make sure. I've already made one mistake on this problem. Yeah. Okay, so the 2 times 10 to the negative 2nd is the Pb concentration times this one's squared, okay? So then once we divide, we're also going to have to take the square root of our answer here. And so the concentration of the chloride for this one is 2.9 times 10 to the negative 2nd. Okay, so there's our two concentrations, and we can compare these to one another. Um, yeah, I mean, it definitely is, right? It takes, oh, no, I'm sorry. Wait. Definitely, I said definitely, and I'm wrong. Here's the thing. Yeah, well, sometimes I hear what you say, and it sounds good, and I'm like, okay, yeah, wait, no, that's not right. Okay, the one that needs the least concentration to start to precipitate is going to be the one that precipitates first, right? Okay, the lead requires a higher concentration of chloride to start precipitating. Does that make sense? Do you guys see that? Okay, so because the Cl minus concentration needed to start precipitating the silver is so low, if we're adding slowly, we're going to get to that concentration first. So the silver chloride is going to precipitate first. Okay, which, looking at the KSPs, you would have guessed that. Okay. Yeah, and you would have accidentally guessed right on that if you weren't paying attention to stoichiometry. But again, this is one where maybe if you were looking at the KSPs and at least had some basis for your answer, then I would give you some credit. But to get full credit on this one, you've got to show me you understand the stoichiometry here. Okay? All right, that's a nice quick one this morning, but that finishes up our solubility unit. So, see you guys in class.